Figure 2-9, the direction and magnitude of the electrostatic field. The electric field at P, due to the surface charge in an infinitesimal element of area in the xy plane. Distance between these 2 points and the infinitesimal space is the element of volume space. Note that during the integration, the point P is fixed, so that the space coordinates must be treated as constants. Frequently, the process of integration can be simplified by writing the integrand in terms of the unit vectors I, j, and k, which provide 3 scalar integrals each multiplied by one of these unit vectors. This process can be illustrated by calculating the electric field near an infinite plane that has a uniform surface density of charge, whose units in meters, kilograms, second systems are coulomb meters squared. Coordinates can be chosen so that the xy plane coincides. The first 2 double integrals are each 0, as should be expected from symmetry considerations, but the third gives the electric field. A field which is independent of the coordinates at all points above the charged plane. Below the plane, the field has the same magnitude but is in the opposite k direction. The foregoing calculations may appear artificial since infinite planes do not exist. However, equation 2-8 is an excellent approximation to the fields at points that are relatively close to a large flat sheet having a uniform surface density of charge. For points less than 0.005 centimeter from its center, a flat disk of 1 centimeter diameter can be assumed. A double integration of the electrostatic field with x and y, each varying from negative to positive infinity, is required to determine the electric field. Since I, j, and k are constants, the electric field can be expressed by 3 scalar double integrals, each multiplied by a unit vector. That is, vector mathematics for electrostatic fields. That upper equation is the line integral, scalar or dot product of vectors 2-8. It has been assumed that scalar and vector quantities can be multiplied together to provide new vectors of different lengths. The question arises whether or not an operation involving the multiplication of one vector by another can be defined to yield useful and consistent results. It will be shown that at least two such operations can be defined. One of the most common operations in physics is to calculate the work done when a given force, F, moves a body a given displacement. If the force is not in the direction of motion, the work done is